Thank you for the introduction. Sorry about the long title. It's actually, this talk is in the same setting as the previous two talks, but this time we're going to look at things from the perspective of attacks. So just to recap the setting quickly, we're considering a case where, as a client, you want to outsource some data to an external server somewhere in the cloud. And you want also to be able to issue search queries on the data that you have outsourced. So for example, if you're thinking of outsourcing a database, you might want to be able to handle basic queries such as fetch all records that match a given value, or fetch all records that are whose value is within a given range. And of course, you might also want to encrypt that data, right? And here you will need to achieve some sort of trade-off between the security of your scheme and the ability for the server to handle a rich set of queries. Because if you were to just encrypt everything naively, then the server would not be able to handle queries. Okay, so which adversaries are we talking about? So the most basic adversaries that you might think of is just a snapshot adversary who would break into the server and steal the memory of the server, observe the memory of the server, and get your database, your encrypted database. But you may also want to consider a stronger adversary, a persistent adversary, who would be able to corrupt the server for a certain amount of time and observe all communication. And moreover, if you want to ensure that your data is private with respect to the server who is handling the queries, then the server itself is your adversary. You want that the server who handles the queries cannot infer the values the values within your database. So this is what the previous two constructions were trying to achieve, right? So in this space, there are already a number of solutions. So you might have heard of a structure preserving encryption, for example, so order revealing encryption or order preserving encryption. Those could be considered as maybe first generation solution. And if you've heard of them, you might also have heard that they are pretty broken. So as a result, there have been second generation schemes that attempt to protect, to give meaningful guarantees against snapshot and persistent attackers. And this is currently a very active research topic. We've just seen some examples in that space. So today specifically, I want to talk about range queries. So beyond queries where you want to fetch a record that matches a fixed value, perhaps the most basic query you want to be able to handle to call something a database management system is range queries. So here in the example that is shown on this slide, you say the server has 4 records, and we're going to focus on one value in each record. So we're going to look essentially as one column in the database. So assume the server has 4 records with the values in red here, and the client issues a query to fetch all records whose value is between 40 and 100. Then in that case, the server would return the first and third record whose value is within the range. But of course, the hard point here is that everything in red in this picture is actually invisible to the server, right? So the server doesn't see the queried range, doesn't see the value of records, and doesn't see the values of the records it returns. So from the point of view of the server, what the server could see is just that it has 4 records. It receives a query, some crypto magic happens, and then the server returns, learns that the records that match these queries are records 1 and 3, and then returns these encrypted records. What you might observe by looking at this example is that actually the server does still learn something, right? Namely, the server learns that there was a range query, and records 1 and 3 did match that range query. And in the literature, this is called access pattern leakage. The reason this is called that way is because while here I've represented the identity of each record by a number from 1 to 4, you could imagine that the identification of a record is its memory address. It is address in memory. And in order to return records 1 and 3, the server would have to access the memories that store these records, unless you use something like oblivious RAM. So it's in many settings, unless you use some advanced techniques to hide access patterns, this sort of leakage is inherent. So most schemes, actually, the vast majority of schemes will leak that information. And in addition, many schemes will leak some additional information. For example, rank leakage, which is the information of how many records are below the value that was queried and how many are above the value that was, the range that was queried. Okay, but we're going to focus mostly in this generic setting where only access pattern is leaked to the server. So most of the schemes that exist in the literature are going to offer security proof. They're going to prove that what is leaked to the server is only a certain formal leakage, for example, access pattern leakage. But the question is okay, you have proved that, but what can the adversary actually learn from that leakage? And so our attacks are not going to contradict the proofs that exist in the literature in all these schemes, but are going to show that from just this leakage, from just access pattern, we can learn a lot of information. So how much information? Actually, our goal is going to fully reconstruct the value of every record in a database. So basically, it's as if there was no encryption at all whatsoever, okay? And our main result is going to do that from just access pattern leakage. In fact, there is already prior art on this. So at CCS 2015, there was a result that showed that you could achieve this using only n² log n queries, where n is the number of distinct values that a record can have. And this is under the assumption that your data is dense. So that result I just mentioned is under the assumption that the data is dense. So what does density mean in that case? It means that every possible value from 1 to n is taken by at least one record in your database. This is an assumption that we're going to make for our main results. In addition, we're also going to assume that the queries that the client makes are uniformly distributed. But I want to insist that this second assumption is only to be able to compute bounds. Our algorithms actually don't need the assumption. We're going to come back to that later. Okay, so all in all, we actually present 3 attacks. I'm going to skip the second one completely in this presentation. And our main result is the first one. So it's the fact that you can reconstruct the value of every record in a database in just n log n queries. So there is a square root improvement over prior arts. And this is in this very generic setting where only access pattern is visible to the server. And then I'm going to briefly present a second attack that takes advantage of more precise information that could be available to the attacker. So how do you do that, right? How can you reconstruct the value of every record in the database from just access pattern? That might look surprising. So I'm going to try to give an ID of the algorithm that we use. So it's just going to be a flavor. I'm not going to give all the details, but just the high-level IDs of the algorithm. So okay, so you have a set of all records that's represented by this gray bar at the top. And now, as the attacker, you see access pattern leakage. So say there is one query for no. The adversary is going to see that that query has matched a certain subset of all records. So this query is represented here by a green bar that matches a certain subset of all records. And in the example I'm going to give, we're going to assume that there are just 7 possible values in the database, so n equals 7. So here there is one query, then a second query is issued, and the server sees that this query matches another subset of records, and so forth. Okay, and now from just these 5 queries, we're going to reconstruct the value of every record in the database. So how does the algorithm work? The first step is that you're going to partition the set of all records. That is, you're going to take all the access pattern leakages from all the queries that you have seen so far. And from these, you're going to build the minimal non-empty subsets of records that can be obtained from these access pattern leakages using basic set operations, such as intersections, unions, set subtractions. And you're going to build all these minimal non-empty subsets that you can build from the leakage you have observed. And the main thing here is these minimal subsets are going to partition the set of all records into subsets. So here the gray bar at the top has been partitioned into 7 subsets. And if these minimal subsets, the number of minimal subsets is n, so in this case 7, then you can immediately deduce that each minimal subset must be the set of records that match a single value in the database. So you might wonder, okay, that's nice, but how many queries do you need to get that? To get that when you build these minimal subsets, then you will have n of them, and so each one of them must correspond to a single value. And the answer to that is that actually, when you do the analysis, this reduces to a variant of the coupon collectors problem. And you get that you only need roughly n log n queries before this partition will actually yield a partition into n distinct non-empty subsets, disjoint. Okay, and when you add this step, you're actually not done, because you might not know, the server might not know which minimal subset corresponds to which value. And to do that, there is a second step in the algorithm that I'm going to just go very quickly over, which is to sort these minimal subsets. To do that, you first find an endpoint of the subsets. And when, to find the endpoint, you find overlapping access pattern leakages whose union covers all subsets but one minimal subset, and then you can deduce from there that this minimal subset must be an endpoint. And then essentially, once you have found an endpoint, you're going to propagate information about the order of minimal subsets such that you find the next minimal subset that is next to the subset you already know. So I'm just going to go very quickly over that. But the high-level idea is that at every step, you're going to build the minimal subset of records that overlaps the minimal subset you already know, and such that you know it is adjacent to the values you already know. And if that minimal subset is actually one of the minimal subsets you had at the partitioning step, you can deduce it's the next value, and you propagate this algorithm until you have recovered every value. So this sounds really complex, right? Like this second step, this sorting step. So you might wonder, okay, how expensive is that in terms of data complexity? Well, the big thing is that it's almost free. So actually, the expensive part is that the partitioning step should yield the partition into n subsets. Once that is the case, this sorting, it is highly likely that you can actually sort all minimal subsets without additional queries, or with very few additional queries. And more precisely, we prove a bound in the article that after the expected number of queries after which you can actually have the partition n sort everything is bounded by n times 3 plus log n. So barely more than what you needed just for the partitioning step. Okay? So one way to look at this result is essentially range queries leak a lot of information about the order of values in a database, such that as soon as you have n distinct minimal subsets, then you can sort them and recover the value of every record. Moreover, we also prove that this bound is optimal up to a factor 2, essentially. The efficiency of the algorithm is actually very high. It doesn't really matter. Like the real measure here is data complexity. And also our algorithm is, so the algorithm I very briefly presented here is also data optimal. And by that, we mean that when you give some query leakage to the algorithm, either it succeeds or it fails. If it succeeds, it's always correct. The output you get is always correct. If it fails, then no correct algorithm can actually recover the order of record from the same input. So it's optimal in an information theoretical sense. So in this setting, you can't do better than this algorithm. And you can bound how many queries you need, essentially within a factor 2 with these 2 bounds. Okay, so this is all in this very generic setting where you have only access pattern leakage. In concrete schemes, you often have more leakage. And I'm going to, for example, you might have rank leakage, in which case you can do, you can actually skip the sorting step. You can still partition your records, but you can skip the sorting step and instead use, if as the attacker you know an approximation of the distribution of the database, you can use that to skip the sorting step and deduce information about the approximate value of records in the database before you have n log n queries, even if you have just a few queries. So I'm going to skip the explanation of that. But the end result is that we run experiments on the real-world hospital databases and looking at the age of patients in a hospital. And even using a very bad approximation of the distribution of the database, we were able to get these results where on the x-axis you have the relative error of the output of the algorithm, where, for example, an error of 0.1 means a 10% mistake in the outputs. And on the vertical axis, you have the proportion of records which achieve that given precision. So for example, here, you see that after 5 queries, then the attack succeeds in getting about 50% of records within a precision of 10%. Just 5 queries, right? So this is pretty devastating. So in conclusion, we presented 2 attacks. So the main attack is that after just n log n queries, you can recover everything. In this very generic setting where you have only access pattern leakage and it's a data optimal algorithm. And concretely, what does that mean? If you look at age data in a hospital, then n equals 125. After just about 800 queries, you can recover the value of every record in the database. Okay, and for comparison, prior work required upwards of 100,000 queries. So this is really much more devastating than what was known prior. And furthermore, in concrete cases where you have an approximation of the distribution and you have rank leakage, so a bit more leakage, after just 25 queries, you can recover a majority of records within 5% in the experiments we did on real-world hospital age data. So I guess the takeaway here is there are many schemes that try to achieve this range query functionality. Some of the second generation schemes can achieve a meaningful amount of security against a snapshot adversary that just steals the memory of the server at one point. But essentially, all schemes that leak access pattern leakage, and that's almost all of them, do not offer any meaningful security against a persistent adversary. So if you're using schemes like that, you have really no meaningful guarantee against the fact that the server cannot learn your data. And in fact, they can after surprisingly few queries. So thank you for your attention.
Okay, we have time for one question.
Yeah, Benedict Stanford. I was wondering whether you think the same algorithms will work if you have sort of a distribution over the access pattern, or if your access patterns are noisy and you don't have perfect access patterns available.
I suppose it depends what type of noise we're considering. My intuition is that in general, like in a very vague sense, because it depends what type of noise we're thinking, it would make the algorithm much more expensive, but still possible. Like that type of attack would still be possible. But it would really depend what type of noise we're talking about. Yeah.
Thank you.
Okay, let's thank Bryce again. Thank you.